Hello everyone, and once again welcome back to the class of fundamentals of particle and fluid solid processing. So, we were discussing on colloids and nanoparticles. We came to this stage that we have seen van der Waals forces, electrical double layer forces, and we introduced the absorbing polymer bridging and the steric forces. So, the reason of these kinds of forces, because if we want to control the surface force between the particles in suspension, sometimes we add soluble polymer into the solution. Now, the solutions and the polymer, it has some interactions. Now, how that happens is that this polymer's affinity to the particle's surface and its tendency to be adsorbed on the particle surface, this creates this kind of forces. Now, how it happens? Depending on the amount of polymer being adsorbed and its molecular weight, we can have attraction or repulsion. Attraction happens by polymer bridging, the repulsion happens due to the steric interactions. So, coming firstly to the interaction part or the attraction part rather here. So, this is called the bridging flocculation. Now, when the polymer quantity that is poured into the solution is less than the minimum that is required to cover the full surface of the particle. In that case, what happens? The polymer chains from one particle's surface extends and adsorbed on another particle surface, and this creates a polymeric bridge in between particles, which is attractive in nature. Now, the optimal amount that is typically given for such kind of attraction to happen, usually which is sufficient to cover half of the total particle surface area. That amount is, we typically say, the optimal amount or the optimum amount that is required to have such kind of attraction or the interparticle forces. Now, polymers, the best quality or the best polymers that exhibit this kind of good attraction are of very high to very high molecular weight, typically in the range of 10 to the power 6 gram per mole. The other aspect of this, that when it is used commercially, these polymer flocculants are typically of charged or non-ionic copolymers of polyacrylate. It has immense application and several extensive applications in liquid solid separation, in water treatment, wastewater treatment, paper and mineral processing industries. What it does, it basically creates attraction between the fine particles that results in the formation of aggregates, also known as flocks, or from flocculations it is flocks. Now, once it is formed, we have seen in the previous sections as well that once these flocks are formed, these are of bigger in size, okay, of or greater mass than the origin fine particle sizes. So, what happens? The body force then becomes dominant in controlling the behavior of these flocks, and then it helps us to separate from the solutions like the gravity sedimentation. It actually then overwhelms the randomizing effect of Brownian motion, so that it cannot diffuse further. We can have easy separation of these fine particles in terms of aggregates or the flocks. Now, this polymer addition can also result in repulsion that we mentioned, or I mentioned, as the steric repulsion or the steric forces. Now, it happens with a steric mechanism. So, what is steric repulsion? Now, when this the particle surfaces are fully covered with these polymers that is adsorbed on the particle surface, It creates a thick layer of polymer, and it also adsorbs into the surface of the particle and extend out to the solution. And then what happens when in a good solvent, when the separation distance between the particles is less than twice the extent of this polymer or the adsorbed layer, then overlapping of this polymeric layer happens, and that results in strong repulsion. A good polymeric solution or the polymer that exhibit this steric repulsion is typically low to moderate molecular weight polymers, usually less than 10 to the power 6 gram per mole of such molecular weight. So, which means the property of these particles can be tailored based on the requirement, that the amount of polymeric material that is being adsorbed on the surface and its molecular weight basically dictates whether that would be the attraction or there would be repulsion. Now, these two scenarios are summarized here in schematic. The figure A shows this polymer bridging, where this is the extent of these polymers that is into the other particle. In this case, it has been extended to the other particles from one particle. So, this is the bridge that has been formed. Now, this happens, as I have mentioned earlier, when say it is partially covered, the surfaces are partially covered with this polymer. It is not fully, and the optimal amount is the half of the area that can cover. So, in that case, it extends to the other particle and forms a bridge, and then it is attractive in nature. But in case of steric repulsion, when it is fully covered with the polymeric layer, okay, it only extend into the solution, not on the other particle. And when this interparticle distance is lower, this cloud actually overlaps, or this layer actually overlaps, and then there is a strong repulsion due to this steric hindrance. There are other forces that are involved in this surface force. For example, say in a very dry air, static charge may result in Coulombic interaction between the particles, but in humid condition, this static charge dissipates rapidly, and in solution, a non-absorbing polymer can result in weak attraction called depletion attraction. In case of say the short range repulsion, say the hydration or structural forces that happens due to the layer of solvent molecules on the particle surface, such as say the water on strongly hydrated surface. In that case, a short range repulsion can appear, because we have a layer of solvent molecules around the particle surface. For example, say water layer that is on a hydrated surface. In case of hydrophobic material, the hydrophobic force can be resulted from the attraction between hydrophobic surfaces. Hydrophobic means poorly weighted surface, that is affinity towards water is very low. So, for example, this hydrophobic surfaces in water can result in droplet coalescence and aggregate formation. So, along with the forces, the dominant forces that we have studied is that were the van der Waals, electrical double layer, steric forces, bridging force, adsorbed forces. We can have this kind of hydrophobic force, short range repulsion force, non-adsorbing polymer that can result in weak attraction called the depletion attraction. These all the forces can be there. Now, what would be the then net interaction force between the particles? So, Deriagin, Landau, Varvey and Overbeek, this together with these names of the scientist called the DLVO theory. It sums up that the total interaction is basically sum of the contribution of van der Waals and ideal interactions. And similarly, all other forces can be just added to those forces to have the total interaction between the two particles. So, basically it is the summation of all interaction forces for which we can have the relation, the expression, theoretical derivations or empirical correlations. So, this figure shows that the force versus the separation distance. Now, say for a certain particle at pH 9, you can see that only say the van der Waals dominates. This van der Waals attractive force dominates. As we increase the acidic nature of that solution, say that means the pH is decreasing. In that case, we can see the steric repulsion, okay, the zeta potential is actually increases and that creates the repulsion, and then basically it overwhelms the van der Waals force. But at a shorter distance, van der Waals always dominates. This schematic shows the force versus separation distance for say the bridging attraction or on the retraction. So, say when there are two particles are there if we make them closer, then there is a small amount of steric repulsion on approach. And if we try to bring them to a separate distance, we try to separate or retract, then we see that there is a long range repulsion attraction forces there. So, long range attractive forces is there, and this van der Waals is just for say to show you its magnitude. So, in this case we can have the long range attractive force on retraction or separation, and in this case this is the short range repulsive force as per this polymer bridging or the steric repulsion. Now, so this is the overall forces, the overview on the overall forces. Now, how it impacts on handling the solids or the particles or the colloids. Now, we have seen that this is the potential energy for the van der Waals and this is the electrical double layer. So, from both the expressions it is clear that the surface force varies linearly with the particle size, where x is the particle size. But the body force depends on the mass of the particle, that increases with the cube of the particle size, because it is the volume multiplied by the density. So, which means the particle is either smaller or bigger, it is the relative value of this body force and this interparticle surface force that is important. It is the relativeness of these two forces that actually dominates its behavior. So, for smaller particle, okay, although these body forces are smaller, but the surface force is what dominates its characteristics. So, say particle surfaces that are interacting with air, if nothing is there, typically the dominant interaction is the attractive van der Waals forces. Either it can happen by this van der Waals interaction, or it can happen also through the capillary bridges that we have seen during the granulation studies. If you remember the structures, the funicular structures, pendular structures, those are the bridges that can form between the particles. There is only mechanism for the repulsion to happen is the electrostatic charging, and that can be caused, say, by friction. So, solid particles are in motion, say in a vessel or in a chamber. So, during its rotation and all this stuff, we can have friction, and that can induce static charges, electrostatic charges. But these have insignificant effect, or this becomes non-significant when the relative humidity of the atmosphere is greater than about 45%, because this electrostatic charge we have mentioned earlier rapidly decreases with humidity. So, that means this cohesive fine powders is the result when it is in contact with air because of this van der Waals and the capillary attraction. And this is also the reason why the group C Geldert particles exhibited strong cohesion of the particles, and it was difficult to fluidize because of this attraction and the fine nature of the particle or the fine sizes of the particles. Now, these surface forces also results in high unconfined yield stresses of the powders, which means it requires a larger dimension of the hopper, that is the storage of these fine particles for its discharge than the free flowing powders. It also influences the bulk density of the fine powders, because this bulk density of the fine powders is dependent on the particle sizes. As the particle size decreases, this loosely packed bulk density also decreases, which may sound a bit of counterintuitive, because say reducing the particle size, one would expect a more and more compact densities. But the point is that this consolidation is facilitated by particle rearrangement into a more denser packing structure. But this stronger attractive forces, okay, than the body forces, because these particles are very small, extremely small. So, there would be very strong attractive forces that would make it difficult to rearrange itself. So, attractive forces basically form stronger bond which hinders such rearrangement that is required for consolidation. So, this is how it influences, it affects the fine particle properties. Now, the difference between the fine powder and the colloids in the liquid is that usually in air, or say in the dry fine powder, when these are exposed to air or some other gases, there is very minimal hydrodynamic drag forces due to the very low viscosity of the air. But in case of liquid, hydrodynamic drag force is actually the dominant mechanism, and we have seen that in our earlier classes. So, it actually influences the particle in the liquid. Now, for a suspension, colloidal suspension or fine particle suspension, we can control the interaction force through the solution chemistry that dictates the suspension behavior. What are the suspension behavior? That is, say, its stability, its sedimentation rate, suspension viscosity, suspension density. These behaviors can be controlled by the solution chemistry. That means use of, say, additives like acids, base, polymer, surfactant that with that addition and its influence, we have seen that how pH can influence the surface charges, how the surface force can be controlled by varying the pH, how the counter ions helps in neutralizing the overall solution. So, this actually provides us a range and magnitude of either controlling repulsion or attraction. So, which means if you want, or if I want to have a dispersed suspension, we have to tune its property, solution property, in such a way that it can be suspended for a longer time, or it can be tuned to settle very quickly if that is required. If that is the solid liquid separation is desired, we can change the solution property and it will quickly settle down. So, by varying these surface forces with the help of additives, we can have a control on the suspension. So, this schematic actually summarizes the properties that influences the solution behavior or the intermolecular forces, surface forces, and this surface forces how it influences the overall solution property or the suspension property. So, here it says, say this is the attractive force and this is the repulsive force summary. So, here say the low zeta potential, that is near isoelectric point, if that the suspension is there with high salt, that is the coagulation is happening and say bridging the polymers, or actually result into attraction of the particles, and then the flocculation or the agglomeration happens. We have the aggregated form of the particles, and this results in aggregation, rapid sedimentation, low density sedimentation, that means that can have a high moisture content, or say the high viscosity and yield stress material or yield stress suspension. In case of high zeta potential, that is away from this isoelectric point, low salt concentration, and say there is polymer cushions, that means whole surface is covered with the polymer that is adsorbed on the surface, that means there is a steric repulsion, we have the repulsive forces between the particles, and that results in the dispersed or say the stabilized dispersion, which where the particles can remain suspended forever. So, that results in individual particles, low settling rate, dense sedimentation or say the low moisture content, and low viscosity suspension or material. So, this is how the solution property can control the attractive or repulsive nature of the force, and respectively this attractive and repulsive force how then translated into the solution behavior or the suspension behavior or the fine particle behavior. Now, if we go into the suspension rheology, that we are talking about its density, viscosity and all this stuff. So, rheology is the area where we study the flow and the deformation of a matter. Now, it actually comprises of a wide range of mechanical behavior, from say the elastic behavior to a simple Newtonian fluid. In elastic behavior, it follows Hooke's law. From there, it can cover the whole range of Newtonian fluid. So, that means it can have the rheology can be studied for say water like viscosity of a Newtonian fluid or Newtonian liquid to say the mortar or the concrete, that kind of suspension and the material. So, in these cases the influencing parameter of this rheology is the volume fraction of the solids in the suspension, the viscosity of the fluid, the surface forces between the particles, and the particle size and its shape. All these parameters influence this suspension geology. Now, what we will do, we will start our understanding on this influence of the first parameter, which is the volume fraction of the solids, without considering the surface forces. That means, when only there is hydrodynamic forces and the Brownian motion is there of the particles, which means the particles are non-interacting, and we say typically this is the hard sphere model or hard sphere approach. So, we will start in the next class our discussion on this hard sphere model to understand the influence of volume fraction in a suspension. That means, the concentration of solid particles in a suspension, how its viscosity mainly changes. There is some interesting behavior that we will be exploring, and again we have to remember that that discussion will be on assuming that these particles are non-interacting in nature. Once we understand that concept, then we will couple this hard sphere approach with the particle interactions or the surface forces. So, I will see you in the next class with that discussions. Until then, thank you for your attention.